Alright, today we're continuing with differentials. We're going to be doing problems where we approximate the height of f of 1.9 given some graph, and we don't even know what the function value is, but we can use the tangent line to approximate what the height is. But before we can do that, I want to go to this picture and get a formula that we're going to be using. So I'm going to derive this formula for you. What I'm going to say about this is that the change in y we determined the other day, given 2 points on this function, this one f or x comma f of x, and this one is, because I'm going along the x-axis here, if travel along further, it'd be x plus change of x comma, then the function value would be whatever value I would get when I plugged in the x plus change of x, so we denote that as f of x plus change of x. So change in y is those two y values subtracted from each other. So f of x plus change of x minus f of x. What we learned in the previous day is that we learned that change in y and dy are approximately equal to each other. So I now can say that dy is approximately f of x plus change of x minus f of x. Remember, my ultimate goal is to find or approximate this new height. So what I'm going to do is I'm going to get this f of x plus change of x by itself. I'm going to do that by adding f of x to both sides. That gives me a new equation of f of x plus change of x is approximately f of x plus dy. Since I don't have any values for dy, what I'm going to do is I'm going to replace dy. Dy, we found out the other day, is equal to f prime of x dx. So the last thing I'm going to do to this equation, which will be the formula I'm going to be using, is I'm going to say that f of x plus change of x is approximately f of x plus f prime of x dx. What I'm going to do is I'm going to copy that onto this page and show you how we're going to use it then. I've got f of x plus change in x, which is approximately equal to f of x plus f prime of x dx. What we're going to be trying to do is find what the function value is at 1.9. I can't see that from the graph. I can't come up with the answer, so what I'm going to use is the tangent line to the curve. I'm going to approximate it using this formula. Well, the one piece of information I know is that it does go through the point 2, 1. So I'm going to use 2 as my x. My change in x, the difference between 2 and 1.9, is negative 0.1. So I'm going to plug 2 in for my x. And my change of x is negative 0.1, which is also going to be my dx. So 2 plus negative 0.1 is 1.9, and that's the height I want to find the function to be at. F of 2 I get from the graph. F of 2 is 1. Plus the derivative of 2 is the slope of the tangent line to the curve, which is down 1 over 1. So that means that f of 1.9 is approximately 1 plus 0.1. That gives me the approximate height to be 1.1. Okay, so I just figured out approximating f of 1.9, and now I'm going to approximate f of 2.04. So I'm going to use the same formula. F of x plus change of x is approximately f of x plus f prime of x dx. This time, again, I only know what the function height is at 2. Except my change in x is what's going to be different. To get 2.04, I need a change of x of 0.04. I'm going to put 2 in for my x's. And again, my dx is the same as my change in x. So dx and change of x are equal to each other. If you missed it on the last video, what I did find was that the slope of this tangent line was down 1 over 1, so the slope at 2 was equal to negative 1. So you need to make sure that you notice that, and that's what I plugged in right here and why I plugged in a negative 1. I'll do that right here as well. So when I plug in negative 1, I have negative 1 times 0.04, and I have f of 2. F of 2 is 1. What I now can say is that f of 2.04 is approximately equal to 1 plus negative 0.04, which would be approximately 0.96. Continuing on, we're going to do another problem like this. Notice this time, though, I'm given g prime. So this is the graph of g prime, and this is the point 3, 3 on the graph of g prime. They give me information about g. G of 3 is 8, and I know that g prime of 3 is 3 from the graph. Alright, we're going to use the differentials to approximate these two values. So I'm going to go back, and this time I'll call it g. I have g of x plus change of x is approximately g of x plus g prime of x dx. Now I'm trying to figure out what g of 2.93 is. I'm going to say g of 3, because that's the only information I have. G of 3 plus, this would be a negative 0.07, is approximately equal to g of 3 plus g prime of 3. And my dx is the same as my change of x, so negative 0.07. So it means g of 2.93 is approximately, well, g of 3 they tell me is 8, plus g prime of 3, I got that from the graph, g prime of 3 is 3, times negative 0.07. So 8 plus 3 times negative 0.07 is, let's go straight to the answer here. Punch that in your calculator, you get 7.79. The second value I'm supposed to find is g of 3.1. So the formula g of x plus change of x is approximately g of x plus g prime x dx. So g of 3 plus, I would do 0.1 this time because I went g of 3.1, is approximately g of 3 plus g prime of 3, and my dx this time is 0.1. So g of 3 is 8 plus g prime of 3 is 3. Well, that's going to give me the answer of 8.3. Okay, in this problem we're going to approximate propagated error. Before I do that, I need to mention that propagated error is the change in x, or the change in y. So we know that change in y is approximately dy. So what we're going to be doing is we're going to be taking a derivative to figure out the approximate propagated error. The measurements of the base of an altitude, the base and altitude of a triangle are found to be 36 and 50 centimeters respectively. So what I now know is that my base is 36 and my height, my altitude is 50. The possible error in each measurement is 0.25. So each measurement, my dBs is what I'm going to call those, is plus or minus 0.25. We need to put plus or minus in front of there because it could be 0.5 above or 0.5 0.25 above or 0.25 below, so we need plus or minuses when we're talking about propagated air. And the same thing for my height. My altitude could be plus or minus 0.25 off as well. What we're going to do is we're going to compute the area. The area of a triangle is 1/2 base times height. I'm supposed to use the differentials to approximate the propagated air, so what I'm going to do is take the derivative to be able to use those differentials. So this is a product rule. I need to say first, and I'll count this as my first term here, and then h as my second term. So first times the derivative of the second, which would be dh, plus the second h times the derivative of the first, which would be 1/2 dv, because I'm taking the derivative of b. What that ends up giving me is that my dA, or my change in A, which is approximately dA, is equal to 1/2 times my base length, which was 36, times my propagated air, plus or minus 0.25, plus my height. My height is 50, times 1/2 times plus or minus 0.25. What this ends up giving me, when I type all this in a calculator, I would get 18 times plus or minus 0.25, plus half of 50 is 25, times plus or minus 0.25. This will give me the answer of plus or minus 10.75 centimeters squared.